Alright, and so in this video, we'll be doing another Codeforces problem called Zero Path. And in this problem, we are given an n by m grid, so n rows and m columns. And we want to know that does there exist a such path such that we start from 1, 1, and we have to go to n, m, and we can only move right or down. We want to know if there exists a path such that the sum of every square that we visit in this grid adds up to 0. So, the way you approach this problem is you think of similar problems, right? And after doing some research, right, because I read the solution, I was like, that's really clever. But is this like, how would you think of that? But, there's a similar problem. And once you understand that similar problem, this question is a little bit more trivial because, that it's very similar. And, it's just, I guess, just a metric of how much experience you have with DP on a grid. But if you have a lot, then this question is really trivial. Anyways, the similar problems that I'm talking about, so that's a one good problem solving strategy is look for similar problems, see how you can relate the solution. Is called the min max DP or min max cost on a grid. It's essentially this question, but instead of like trying to see if there exists a path that adds up to 0, you're trying to find the maximum sum of all possible paths. So imagine you have path 1 was like adds up to 10, path 2 adds up to 20, right? Let's say these were all the paths, obviously it's not here, but there's more than two paths. But then the answer would be 20, right? If you're trying to maximize. And if you're trying to minimize, the answer would be 10. So you're more concerned with maximizing and minimizing rather than just seeing if there's a path that adds up to 0. And this is actually this is very important here. This is actually how we solve the question. And so, you don't really have any ideas for what to do now. You might as well just think about how these questions are solved, and then maybe it, inspires such a solution. So let's look at how to solve the min-max cost on a grid. So let's say we have these dots. Boop, 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 boop. Okay, that's not straight. Boop, 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 boop. Okay, right. So let's say we have these dots, right? And this is not straight, kind of irking me. But the idea is that we want to pick any such dot, right? And we want to know, okay, what is the minimum such cost or the maximum such cost? It doesn't really matter. They're both essentially the same question, involve the same algorithm. But no, the minimum slash maximum cost that it takes for us to get to that dot, right? And there's many such paths that we can go. Obviously, we can't, brute force all possible paths. It's not going to work. So we need to optimize this with DP, maybe, right? This inspires some sort of DP relationship. And this question is inherently like recursive in a way because think about it. Let's say I start from this dot here, right? And there's obviously some edge cases, right? If I want to go here, then like the minimum such path is just the value on this dot, which might be 10, the value on this dot, which is 23. There's only one path, right? You just go down. You can't like go here because that involves an operation such that you go left and you can only go right or down. So there are some edge cases, but that's something you just deal with in the code, so you don't get any bugs and errors. But the main juice is that if we pick like maybe a question here, so let's just say this has value 1, value 2, value 3, and value 4. So the possible such paths that you can do is this one, and the possible paths you can do is this guy over here. So let's first just make some easy observations. You would agree that I'm going to label all these points, by the way. So let's say this is the first dot. So I'll just label this, right? So let's say this is the first dot. Okay, so basically basically for any value v sub n will correspond to the dot that I'm talking about. So this is the first one, the second one, the third one, and the fourth one, right? Just so you understand when I, talk about it. So you would agree that for the first dot, right? For the first dot that I labeled, right? The minimum cost is just v sub 1, right? To get to that dot, right? The minimum cost is v sub 1. Let's just talk about the min problem, then I'll talk about how max problem works. It's the same thing. But essentially the cost there on v sub 1 is just 1. And then the cost on, so that's the minimum cost, right? And then for 2, right, it would be v sub 1 plus v sub 2 on the second dot. So for this dot, right, it would be v sub 1 plus v sub 2 because you have this is just there's no other way, there's no other path that gets you to that dot because you can only move right or down, and you can't move like up, so you can't just like move down and then like find a way. There's just no way. That's the only path. And then you note that for the third dot, so this one over here, the minimum is just v sub 1 plus v sub 3, right? And then you're trying to find v sub 4. Well, okay, so there's two different ways to get to the v sub 4. You can either choose to go like v sub 1, right? You can either choose to go this way, and if you choose to go this way, it's a v sub 1 plus v sub 3, um, and then plus a v sub 4, right? Or you can try to go this way. So uh, you want so essentially for this one you want the minimum, right? So v sub 1 plus v sub 2 plus v sub 4. And what's interesting about this is that, well, okay, regardless of which one we choose, we know v sub 4 is going to get added anyway, so let's just do that outside, right? Makes sense. And what's interesting is that isn't this just the minimum of 2? So we can reduce this to the minimum of 2 and 3 plus v sub 4, right? So we start now. Now we make the claim like that. We want to make the claim that if you want the minimum cost, so the minimum cost at ij, right? All we need to know is the minimum cost that, since this is 2, the minimum cost that it took for 2, but in this case, if you're making a general, it's just one row above, so just minimum of I minus 1 j, minimum of y minus 1j. We want the minimum of this, but we want the minimum of minimums, right? The minimum of this, and then obviously that's v sub 2. We also have 3 here. So for 3, it would just be the one to the left. So you would just proceed by doing I and then j minus 1. You want to know, this is what you claim, and then obviously you have to add this v sub 4. But v sub 4 would just be the value, so the value at ij. And this is basically how we derive the minimum cost solution, right? We just literally took a very basic example, like literally this dot, v sub 4, and this is the answer. And we should suspect that this works for everything, right? Um, so, did I? Oh, wait. I need this okay, this should be the minimum. So let me actually write this in here. So the minimum of these guys. Plus, okay. So that's basically the minimum of this and that. So it's basically, in short, it's a minimum of the cost from the one above and from the one to the left. And this makes sense because if you're ever going to visit any dot, right, it works for any dot, and not just v sub 4, you're obviously going to have to come here from the right or go down, right? So you always go there. So if you know the minimum for this guy and the minimum from that guy, you can just take the minimums and then just add it to this guy, which they share in common. And to do this for the max problem, you know what we really do? We just do min dot replace max, okay? So it's the same thing for the max problem. But once you get this, then this problem is not bad, and this honestly isn't really too hard to understand. This is like basic stuff. Just note that you can only come from the left or from above, so you obviously want to take the minimum of those, and this is where the DP takes in hand. So now that we know how to find min and max in an O of n space, O of n time complexity, because this is going to take O of n. If you just like spam this across every single element, it would take O of n. Obviously, there's some edge cases to fill like these ones, but don't worry about that. That's more of good code stuff. But now that we know how to do that, how is that going to help us with this problem? So what do we know? We know how to get the min for anything ij. So if we know how to get the min for ij, then we should know how to get the min for nm, right? So we know the min for mm and max rent, right? We know the max cost and the min cost for this cell, right? So you know what? This is the intuition. This is kind of the beauty of this question. In my question is just having that intuition. The intuition is that if I know the minimum and max cost, shouldn't I intuitively say that if zero is within the min, right, and it's within the max, so it's this is true. Shouldn't this hold? This is and also one edge case that I forgot to talk about is we obviously know there's not going to exist paths. Like if we have like here we have 1, 2, 3, 4, 5, 6, but if we have like five cells, then we know that that's not possible because we have to have an even amount of squares because it has to add up to zero. So there has to be like, let's say if there's n squares, right? We need n over two negative ones and n over two ones, and so n has to be even. But that's an edge case you can talk worry about in your code, and I suggest you actually code this yourself, um, and like worry about that edge case. Um, although this code the code for this is not even that important, so you don't actually have to just understand the logic honestly. But anyways, we should suspect that maybe there's something going on. I mean, it seems intuitive though. But in a code forces question, I would just code this up and then just see if it passes test case and then just screw it and just go for it. But how do we actually prove this? Because many of y'all obviously want to prove this. I mean, it is kind of intuitive, and but and honestly, maybe you didn't think of this, and that honestly, the only way to think of like this is kind of intuition is kind of. I think this is kind of the wishful thinking method where you're like, I wish this was true because if this is true, then we solve the problem. So let's kind of wish that something is true that will help us solve the solution and just see if we can prove it. And it's not like we're making a too big of a jump, right? We're just saying that if zero is between the min and max, then it works, right? Because it makes sense that it's like this, right? So how would we prove this? Well, notice that like let's say a path is we have to go to the right, we have to go to the right, and then we have to go down, down, right? I'm not even going to visually do it, right? And let me note that if this is one such path, then other paths are like, in fact, I'm going to just make this simple. So there's only so there this is there's four choose two ways, to get all possible paths. Right. So let's just do another one. Let's do all ones. So RD RD DR. Okay. And then I want to do DR, and then DDRR, and then DRRD D or D. I think these are all possible paths. Anyways, even if they're not, I don't really care. D R D R. Okay, so 1, 2, 3, 4, 5, 6. Okay, so these are all possible paths, right? So the way you prove this to yourself is, I mean, you note that like, look, let's like every path is going to differ by either zero, two, is going to differ by either zero or two, because like let's say you want to swap, like you want to do RDRD. So where's RDRD? So this one. So if you look at paths one and two, right? One and two are basically you swap the middle two, right? If you're swapping the middle two, well, like I need to show this visually on a grid, right? Let's say you go here. So for this guy, if you see my cursor, if I decide to just swap it with this guy, so instead of going down, I go to the right. Well, you notice that the values here differ by two. So you note that that path differs by two. But let's say I want to do another case. So let's say instead of I'm trying to find another case, but it differs by two. So it's basically going to differ by two numbers, right? It's going to be like a value on this grid minus another value on the grid. So it's going to be either like 1 minus minus 1, negative 1 minus 1. And it's basically just only going to differ by 0 or 2. So the idea is that if it's only going to differ by like 0 or 2, then if this value is achievable and this value is achievable, then we know that we should be able to get min to max by a sequence of any operation of like swapping, right? That there doesn't like of all these combinations that I said, right? there should be a trend, like we should be able to get every single even value, right? Assuming that these are even, we should be able to get every even value because we can either choose to decrease it by 2 or not at all. So that's kind of the intuition, is that you can for each patch you can construct, you can always like choose a combination such that you can decrease it by 2 and or increase it by 2, right? So first here we can choose a combination to decrease it by 2 until we get to the min, or here we can choose a combination to increase it by 2 until we get to the max. And you can always do that. You can kind of play around with it. But that's the intuition, um, is that you could do that. So this kind of reminds me of, like, continuous functions in math, where if you have like a continuous function, then I think it's like the intermediate value theorem. So it's eerily related to that, honestly. But I don't even know if there's like some weird connection with them. But this reminds you of that. But that's the intuition. I hope this video wasn't too long. But anyways, this wasn't a formal proof, but it's just to kind of get your mind to a little wrap around it. But anyways, we did more than just one problem. We also solved the min max cost TP problem. So I'll probably put that in the title: min max cost TP problem with an example, I guess. And yeah.